Aeration is probably the most commonly used form of getting oxygen into the water for the folks here at this conference. A lot of us are using densities that are less than half a pound per gallon, and aeration works very efficiently when you have fish densities of around 0.3 pounds per gallon in your fish tanks. And basically, have you all seen these types of devices before? Yes? Okay. I'm surprised I don't have a red dot on me right now. Martin's sitting in the back here with Fuji Mac, and I got a Nito blower up here.
Yeah, where's the Fuji Mac?
Yeah, that's right. But these two, the air pumps and the regenerative blowers are commonly used for your aquaponic setups. If you're using mixed media bed bioreactors, the air pump is typically tied in with that to provide the aeration for it. Regenerative blowers, you may have seen those tied into the fish production side of things, also with your hydroponic grow beds, depending on how big they are. Those are typically used to supply that volume of air. What they do is they just take the air that you and I breathe, they pressurize it to a small extent, and they push that volume of air into the water. And when partnered with the right diffuser, that volume of air is introduced to the water in a small to medium-sized particle bubble so it's a small bubble with a large surface area, and as it diffuses and rises up into the water, that oxygen is transferred in. So that's the goal with these devices, is to introduce the air that you and I are breathing into the water, and the diffusers aid in that, as seen in the photo off to the left. That's an AI image, by the way. I'm sure you can tell, but I was amazed. I started using it about a month ago and was able to direct a computer to make a diffuser for me. It's pretty amazing stuff. So. The benefits of using regenerative blowers in aquaculture: you can introduce a high volume of air over a short period of time. Often these are measured in liters per minute or cubic feet per minute. They have an efficient transfer rate of oxygen depending on the diffusers that you use. Commonly the silica-based, the glass diffusers are used, but there's some plastic EPDM type diffusers that can be used for different applications in the system as well. They're relatively low maintenance and pretty quiet operation. Have you all been into a facility where as soon as you open the door, you start hearing a whistling sound? No? Yes? Yeah. Well, when you stand next to these devices, you can actually have a conversation. You just have to raise your voice a little bit because they're at about 50 to 60 decibels. But you can stand next to one and you can have a discussion. But it does have a high ringing sound associated with them. The scalability, there's a variety of motor sizes depending on the application. So you can go from 1/3 of a horsepower all the way up to over 10 horsepower, approaching 20 horsepower on some of these units. So for hatcheries and different grow out facilities, depending on the volumes of water and densities you're working with, they're versatile. The configuration of them, you can mount them horizontally, typically is the way that they're done, but they can be mounted in a vertical position too, as pictured in the lower photo. So they can be mounted on a wall vertically so they don't eat up floor space, and they can be up and off the floor and above the water level for the fish tanks or the hydroponic systems that they're supplying, so that in the event they shut off, you don't get a reverse suction and flood out the unit. They can also be located indoors or outdoors. Some people prefer to have them outside of the facility. If you do, you want to have them sheltered. They do have an air filter on the inlet side to keep out particles. But moisture and snow, and if you're real close to a dusty road, it is good to have them in an enclosure where they are somewhat protected. As far as the maintenance and operation, they're very efficient. I know people who use, traditionally for aquaculture, there's a brand out there called Sweetwater, and those regenerative blowers have been known to operate for well over 10 years. And I know people who have them still going 15 to 20 years, and they've never changed the bearings on them. And they have an additional little squeal to them, but they will last a long time. And what is recommended for the regenerative blowers is that the bearings be replaced every few years, so that that shaft can continue to spin and that flywheel can pressurize the air efficiently. So that's really the only maintenance other than having to clean the air filter, which is pictured there with the black object. That's on the inlet side of the regenerative blower, drawing in the atmospheric air. You also want to clean the diffusers on the outlet side of them, so that doesn't cause any back pressure. You don't want to close any valves. These are pushing a high volume of air, just like a water pump. You don't want to close off a main valve in the main distribution area and like deadhead it, because now that volume of air has nowhere to be expelled to, and it creates a big back pressure on the unit itself. And once it is installed in the original design of the system, you don't want to later go on and radically change that air distribution. You may have to replace that over time. Maybe something backs up and cracks it or something like that. It has to be replaced, but you don't want to drastically change the size of the piping. So what determines the volume of air that's required? In general, it's the fish biomass in the tank. Again, these are applicable to fish biomass that's up to about half a pound per gallon at max in the tank. Generally though, safe levels are around 0.3 pounds per gallon. Water temperature is important because warm water holds less oxygen than cold water, so that's taken into account as well when we're sizing these up. Freshwater or saltwater application. Saltwater has dissolved minerals in it, so there's less opportunity for oxygen to remain in solution in it compared to fresh water. And also elevation above sea level. Less oxygen at higher elevations, so usually there's an additional percentage that we take into account when we're sizing these up if you're at elevation. Usually that comes into account when you're maybe 3,000 feet above sea level.
Here's what I found.
Oh, you got some information too? And feel free to share. What determines the regenerative blower size? So it's not only the volume of air that's required, but it's also the pressure loss in the system. And that's to be expected. There's going to be pressure loss. And that's from the water depth that the blower has to overcome to get that volume of air into the water. It comes from the diffusers as well that are tied into that distribution system. And it is dependent on the distribution system itself, which is really where this talk's going to kind of concentrate on, is the volume, or I'm sorry, the positioning of the blower in relation to where the main line is going to be run. So the distance that the blower is from the system before it splits off is all important factors to keep in mind. Now, when it comes to sizing these, there's a lot of folks at the show this week up in the exhibitor center that can size these appropriately for you. But once it's sized appropriately and it's delivered to your facility, it's up to you to make sure that the distribution system is set up appropriately according to the recommendations, so that the volume of air can flow in a sense freely to its point of discharge. And that's where we've walked into facilities and we've seen that there's problems. It isn't that the blower is necessarily under or oversized, it's that maybe the farmer or the research facility has a boneyard of PVC sitting somewhere, and rather than going to Home Depot or another box store and picking up the PVC that would actually be appropriate, they're just trying to recycle what's available, and that can run into problems at times. And what it comes down to is that it's the location of the blower and the run that air has to make. The distance, if the blower's over here at this door and it has to go to the other door. That distance has an effect on the friction loss that occurs for that volume of air to pass through the PVC. And friction loss results in heat buildup, and it can be problematic for the PVC pipe over time. And it's definitely a problem for your blower, because your blower has to overcome that friction that it's trying to push against an undersized pipe. And that can be a problem leading to failure of the blower over time. So making sure that you have the correct size pipe on the discharge side of the blower is real important for these systems. Has anybody ever opened a catalog and tried to size up a regenerative blower before? Yeah, just trying to understand the curves. Is there a misunderstanding of the curves as far as, what's that?
I would say, may I ask a question?
Sure.
What if you have different levels for the fish tanks and you have different pressures? How you could interpret this chart depending on your system?
Sure. I would always size up a regenerative blower for the deepest portion. And then with some valves positioned appropriately, you can distribute the flow of air accordingly. Yeah. But you always have to overcome the deepest portion of the system. Yep, first. So there's actually 3 different curves in these graphs here, and we'll go through them real quick. But when it comes to sizing up blowers, typically on the x-axis, you have the inches of water that you're trying to overcome. And then on the left side, on the y-axis, you have your cubic feet per minute, or sometimes it's liters per minute as well. And that's the volume of air that you're trying to push into the water. And in this first example here, we have a blower that on the bottom, it's 20 inches of water depth, the equivalent of 20 inches of water depth that it's trying to overcome. And at that water depth, it can put out, roughly 42 cubic feet per minute. Now that it's not only the inches of water that blower is trying to overcome, it's the equivalent inches of water that has to be pushed through the diffuser as well. So you may actually have 20 inches of water, but that diffuser has pressure in it as well, usually in pounds per square inch, that can be converted to the equivalent of water depth. And the blower has to overcome that. So it's not just simply measuring your water depth in the tank and trying to size up a blower. It's also knowing what the pressure loss is through the air stones or the diffusers that you've chosen. Usually the Sweetwater diffusers are an additional 10 to 12 inches of water. So in this next example here, we can use this as an example, including the diffusers. On the bottom, it's trying to overcome 40 inches of water depth. Now, 40 inches of water depth would be the equivalent of, say, 24 inches of actual water depth with an additional 12 inches of water depth for a silica-based glass diffuser. So that would be roughly 40 inches of water. And it would be able to put out 30 cubic feet per minute under that scenario.
So if I have like a Sweetwater diffuser, it's like a 9-inch diffuser, it says it has 0.75 cubic feet per minute. Is that, and then I have my friction loss in my pipe, and then I know my water depth, I'm trying to aerate. Is that what you mean by the pressure that goes through the blower, or is that, through the air stone, or is that a separate calculation?
Well, overall, the blowers are going to be able to, like in this scenario, the blower is trying to put out 30 CFM, 40 inches of water, and that accounts for your depth of water, the pressure loss through the air stone.
Which is the pore size or whatever, right?
Yeah, generally the medium-sized, the medium pore air stones that you get from Sweetwater, they have a pressure loss the equivalent of 10 to 12 inches of water. So if your water depth is 20 inches, your blower doesn't just have to overcome the water depth, it needs to overcome the pressure loss through the diffuser too. So it's the 20 inches of water, and it's the 10 to 12 additional inches of water, the equivalent of pressure loss through that diffuser. So the blower has to be able to put out 30 CFM in the equivalent of 32 inches of water
That's per.
per air stone. Yep. And so that's just the pressure. And then in terms of the volume of air, it's 0.75 times however many air stones you have. So in this case, we know that it can, if the water depth is 30 inches of water, and there's an additional 10 inches due to pressure loss through those air stones, we're talking about 40 inches, right, of water depth. So you take 30, you put out 30 CFM, you know that your air stone can put out 0.75 CFM. So you take 30, divide that by 0.75, and that tells you that, I don't know what that comes out to, 35, 36 air stones, whatever, maybe.
And then you add a buffer or no?
There's already some buffer there.
Okay.
Yeah. Now, where you want to be careful is the next step is what, no, that's all right. It's the next step. And this is what happens is that either a farmer who's understands this or a farmer who calls in and say my group helps them out, will size up a blower, they'll receive the blower, and the blower should work for the application that's been discussed. But then the farmer will sometimes change the size of the distribution pipe, and that's where we run into problems. Yeah, or they'll modify the way the air is being distributed, and that will result in the problems. Yeah, so we want to reduce that friction loss through the PVC pipe. So this one off to the right, again, the lower right, we have the inches of water, we have the cubic feet per minute on the y-axis on the left-hand side of the graph. Just so you know, these regenerative blowers, they can run at 50 or 60 hertz. So when, for example, if you're running in the European countries, Sweetwater blowers, they can run at 50 hertz, but the output is less. Okay, so here it's labeled 60 hertz, so we're looking at the solid line. Same thing over there, we're looking at the solid line for 60 hertz. So this one we can do 40 inches of water, we can do 150 cubic feet per minute, is what the red line is showing us, where those two converge. And then that's for a 2.8 horsepower blower. And then for a 3.5 horsepower blower, it can do 80 inches of water, it can do 100 CFM. So you can see that as the water depth increases, the volume of air that can enter into the water is less for these units. And that makes sense. It's more pressure, that water depth that the air has to be pushed through. As that increases, the volume of air that blower can push into the water decreases. It's an inverse relationship. So let's just take a quick look at a couple different scenarios. In this scenario, we have a blower on the left-hand side, and it is going to be pushing a certain volume of air 100 feet to an aquaponic system. Let's assume that the hydroponic raceways are located off to the right-hand side, and that's the distribution center for the air to be distributed into the hydroponic raceways off to the right. But the distance between those locations is 100 feet. Martin, don't hurt me, man. This is a high blow one, okay? So it was just convenient. So this is a a simple chart that helps to explain volume of air in trying to overcome the pressure loss through PVC pipe. So let's take a look at it. On the left-hand side is the volume of air, the cubic feet per minute. Sometimes, again, that's liters per minute, but here it's cubic feet per minute. Up top is the pipe size that the air volume has to pass through. Anywhere from 1/4 of an inch up to 6 inches is what this particular chart covers. But more commonly in aquaponics and aquaculture, we're talking, 1/2-inch pipe up to maybe 3 inches in diameter PVC. So we'll concentrate on that area. It's expressed as pounds per square inch up top there, PSI, pounds per square inch per 100 feet, okay? So here, pounds per square inch, it doesn't really equate well with the way blower curves are set up when we're talking inches of water, so we need to convert that, and it's a simple conversion. 1 PSI is the equivalent to 27.7 inches of water, okay? So we'll keep that in mind as we do these calculations. So let's assume that we have a small blower or a large air pump that can put out 10 cubic feet per minute. And we look at the range of pipe that we're working with from 1/2 inch up to 3 inch. And there's some numbers in some of those columns associated with that volume of air. But it's in PSI. So this first one, you can see at 1/2 inch, 10 CFM, 1/2 inch of PVC pipe. It's 2.42 PSI. Again, when you're sizing up a blower, when they're talking inches of water, it requires a conversion. So we can do that. 1 PSI is 27.7 inches of water. So we have 2.42 PSI here. So we convert that, and now it's 67 inches of water. And 10 CFM, the pressure loss at 100 feet of pipe for 3/4 inch is 16.9 inches of water. The pressure loss for 10 CFM at 1 inch of pipe is 5.3 inches of water. So the point is that as you increase your pipe size over longer runs, you have less friction loss. There's no air pump that I know of that can put out 10 CFM at 67 inches of water. That thing is going to be turning on, and it's going to have no way of, if your air stone is at 67 inches of water, it isn't the case, but if you can imagine that, that pump will be operating, but it can't discharge that volume of air into that depth. There's going to be a lot of back pressure on that pump, that air pump. It's going to heat up, and components inside are going to fail, and that unit's going to fail. However, if it's located down here and the discharge is down there, it's 100 feet from the point of discharge. If you use 1.25 pipe, then that volume of air, 10 CFM, traveling through 1.25 pipe, you're only going to lose the equivalent of about 1.5 inches, which isn't that much. That can be built in to sizing up an air pump. Does that make sense to people? Yeah? Okay, very good. So you never want to go below. You don't use 1/4 inch, don't use 3/8 inch, because 1/2 inch isn't going to work. And you don't necessarily need to go above 1.5 inch, or I'm sorry, 1.25 inch for a small air pump. So don't use 1.5 inch, don't use 2-inch pipe. There could be costs associated with that depending on where the placement is. Most of the time, though, these small air pumps are right next to the area that they're going to be discharging into. So now let's look at 50 CFM. When we convert the PSI to inches of water, 50 CFM, 1.5 inch pipe, 50 CFM traveling through 100 feet of 1.5 inch pipe is equivalent of an additional 11.9 inches of water. At 2 inches, at 2-inch PVC pipe, 100 feet of that, there's an additional 3.6 inches of water. And at 3 inches or 3-inch PVC pipe, we're looking at about 1/2 inch of additional pressure on that blower. So a lot of blowers that are putting out 50 CFM, they are, the outlet to those is already 1.5 to 2 inches in size. So the point is, don't downsize that. Don't go from 1.5 inch outlet down to a 1 inch. You're gonna run into problems. And you know, once you get above 3 inches, you're just looking at additional costs. So you know, operating in the for 50 CFM, if it's a 100-foot run, operating in the 2 to 3 inch range for PVC pipe on that long of a run is an ideal spot to be. Now, with all things being the same, let's just shorten the run. Let's just go to 10 feet. So if you walk into facilities, oftentimes the hydroponic grow area could be here, and the blower could be right over here in the corner. It's not located way down at the end of the facility. If you think of a 30 by 96 greenhouse, oftentimes the blower may be located in the middle and it's split. So let's see if we can put the blower a little bit closer to the points of discharge and see what that does. Same chart, we got cubic feet per minute on the left. We got the pipe size up top. We'll concentrate on the 1/2 inch to 3 inch for these calculations. The only thing that's changing is the pipe run. So this chart again is expressed in pounds per square inch. This time we're just going to do some conversions and convert that pipe run to 10 feet rather than 100 feet. Keeping in mind 1 PSI is equal to 27.7 inches. Everybody awake? People falling asleep with this? This is like a long lecture, right? Oh my gosh. Just,
pump is.
yeah, okay. Okay. So at 10 CFM, and it's located only 10 feet away, it's the same pressure again, because this chart is for 100 feet, remember? So now we do the conversion. Everything is 1/10 of what it was, because 10 is 1/10 of 100. So the pressure loss for something that's trying to put out 10 CFM in a 1/2 inch pipe is now only 6.7 inches instead of 67 inches. For 1 inch pipe, rather than 5 inches, it is only 1/2 inch. So the closer you can put this to the point of discharge, the better off you may be in reducing that friction loss. Again, you don't want to undersize or oversize. It can be costly. Looking at 50 CFM, when we convert that to inches of water for a blower that's located 10 feet away from the first point of discharge or where it's split down the hydroponic raceways, you know, 1.5 inch pipe, you're only losing 1.2 inches of water. So if the water depth is 20 inches, you're using a silica-based air stone, which has the equivalent of 10 inches of loss. We're at 30 inches of water there. With the pressure loss through 1.5 inch pipe for that 50 CFM, we're at about 31.5 inches of pressure loss. So now we can go back to that curve. We can look at depth of water equivalent to 31.5 inches and what the output is for a blower at that depth. So in conclusion, regenerative blowers are a great option for aquaculture purposes. For a lot of folks here, the densities you're working at, for incorporation into your aquaculture component and your hydroponic component, regenerative blowers and linear piston air pumps work great. When it comes to sizing them, fish biomass is important. The environment that you're growing them in, whether it's warm water or cold water, fresh water, salt water is important to take into effect. And the elevation you are above sea level. You want to minimize and maintain the design pressure loss. So there's expected pressure loss in the system. That's through the water depth and with the type of air stone that you're using. What you want to prevent is restricting the outlet size, the PVC pipe, and downsizing that on the outlet of the blower. If the blower has a 1.5 inch outlet, you want to try and go to the next size up. You want to try and go to 2-inch PVC pipe. The blower location is important. The closer you can locate it to your points of discharge, the better off you'll be, because that friction loss through the piping will be reduced. You never want to restrict the outlet of a blower. Can't stress that enough. Don't downsize the pipe on the outlet side of the blower. Always try and go up to the next size. Don't deadhead the airflow. So if you have a ball valve somewhere in your distribution, you don't want to shut that off, because now that volume of air has to be shifted somewhere. If it's on the main line, it has nowhere to go. The blower's just pushing against a ball valve. And then if it's on your distribution going down your raceways, if you shut off 2 of those raceways, don't expect that volume of air that's been going down those 2 raceways to just automatically shift to another portion of your system. There's going to be a lot of back pressure on that blower as a result of you shutting those off. So it's best just to remove your air stones, clean them quickly, put them back in place, rather than shutting off main plumbing throughout the distribution. And then definitely clean your air stones. You're going to get biofouling and scaling on them, so going through a regular maintenance schedule of like a muriatic acid dip or something like that, get that biofouling off, get that scaling off. It's just going to allow the air to diffuse into the water more efficiently and prevent any back pressure on that system. So, are there any questions?
Yes.
Yes, sir.
You would.
Yep.
Oh,
Yes.
Well, okay, at the facility I used to work at, we had a blower, I don't know the horsepower, but it was in an outside building, and it would get so hot in there to the point where it would melt the PVC pipe. So what we did is we added metal piping to get it outside, and then we had like almost like a 6-inch air duct that it would go through to help diffuse the heat, and then it would go to like 2-inch PVC. So does that air duct, would it reduce the amount of pressure? And so like we would need
Like
even more horsepower?
You have the heat dissipation pipe, a bigger, rounder pipe?
Yeah, it was like metal,
Uh-huh.
like an air duct kind of.
That would not increase the pressure.
Would it decrease the pressure of it going
I mean,
to the tank?
Overall, very, very minor.
But not, okay, so.
Yeah,
it'd be
it would,
negligible, okay.
yeah. These units do create heat. You don't want to put them in a situation where they're creating more heat than what they normally do. Hence the title of my talk, what's all the hot air about? Because if there's back pressure on these, they're going to create a lot of hot air, and it'll be bad for the unit, potentially your system as well. So those heat dissipation pipes can be commonly installed as a way to dissipate some of the heat generated from the unit itself.
But it's not gonna reduce the pressure that was.
No, very, very,
Okay.
very little.
Awesome, thank you.
What would you recommend as far as replacing pipes? Because PVC Schedule 40 pipe has gotten a little bit burned out on the very starting point of the blower, but the rest of the pipe, like maybe 3-foot long pipe, needs to be replaced. What would be this?
Yeah, if you could get local metal fabrication shop, if it's 1.5-inch outlet on your
3
blower,
inches.
3 inches. Yeah, I mean, a 3-foot section, if they could thread it on one end, you can then put it into the outlet of the blower, and then you could use like a rubber coupling to get the metal connected to your PVC, then you'd be better off. Yeah.
Like Fernco couplers will do.
I'm sorry?
Fernco?
Fernco or, radiator hose is more commonly used. Yeah, yep, yes.
When you guys design systems, do you recommend having separate blowers for your fish, like for aquaponics production, for your fish and your plants?
Depending on the size of the system, it might be a benefit, but it can be sized appropriately, and with ball valves placed in the right spot, you can distribute air where one blower is powering everything.
Just like thinking about what you were talking about, the amount you need, the friction loss between a 100-foot pipe through a greenhouse or something like that, that maybe cost effectively, you might be able to have 2 smaller blowers doing the same job, but maybe that's more money, I don't know.
Yeah, I mean, when I was at the University of Virgin Islands, we had 2 different blowers. I think it just came down to efficiency, cost for that, yeah. But, so there's different ways to look at it. I have time for, I apologize, just for one more question. I'll take it. I know he's been raising his hand. I'll catch you on the side if that's okay.
Okay, yeah, that's fine.
Yeah? Yeah, go ahead.
Yeah, I just had a question about how to interpret pressure gauges downstream of the system. That, you know, reading net positive pressure of, let's say, 2 PSI pipe after the blower. Is that an indication of the available pressure at the air zones, or is that excess pressure in addition? I basically like to figure out how much back pressure we've got, how much our budget is for getting the pressures out.
Sure. I would interpret that as total.
Okay.
That's reading the total pressure that's being put back on that gauge.
Got it.
Yeah.
Okay.
Mhm.
Like it's-
Okay. So, love the questions. I'm glad those questions were on topic because I wasn't sure if it was sinking in with everybody. You know, sometimes, you know, the feedback you get on some of that stuff isn't always the best. So thanks for getting through that talk with me.